Hi, I'm Bob. Thank you so much for watching the teaching videos and doing the computer exercises with me. Let's continue our solutions to the last 7 exercises today for Chapter 17, Limited Dependent Variables Models and Sample Selection Corrections. Let's go to Computer Exercise 11. The data are for married women. We also have information on each husband's income and demographics. In Part 1, what fraction of the women report being in the labor force? We use the tabulate command to find information on the Darby variable. Of 5,634 women in the sample, 3,286 are in the labor force. In Part 2, using only the data for working women, estimate the wage equation by ordinary least squares. Report the results in the usual form. Do there appear to be significant wage differences by race and ethnicity? We use the regress command to estimate the model by OLS. Since there is no wage data for women not in the labor force, the wage equation only contains data for the 3,286 working women. The coefficients on Black and Hispanic variables are not individually significant at the 10% level. They are not jointly significant either, according to the F-test. There is no evidence of wage differences by race and ethnicity. In Part 3, estimate a probit model for labor force participation that includes the explanatory variables in the wage equation from Part 2 and no wife income and kids less than 6 years old. Do these last 2 variables have coefficients of the expected sign? Are they statistically significant? We use the probit command to estimate a probit model for labor force participation. The labor force participation equation contains all 5,634 women in the sample. The 2 additional explanatory variables have the expected signs. More non-wife income and more young children will reduce the women's probability of working. Both are statistically significant at the 1% level. In Part 4, explain why, for testing and possibly correcting the wage equation for selection into the workforce, it is important for the non-wife income and the kids less than 6 years old to help explain labor force participation. What must you assume about non-wife income and kids less than 6 years old in the wage equation? As explained in the textbook, the inclusion of additional exogenous explanatory variables in the selection equation helps alleviate the multicollinearity problem in the second stage regression when we add the inverse Mills ratio to the wage equation. Without additional explanatory variables in the first stage, the inverse Mills ratio is very likely to be highly correlated with the explanatory variables in the second stage. And this multicollinearity leads to high standard errors for the estimates. The estimates are not precise as a result. So we should have at least 1 additional explanatory variables in the labor force participation equation, but not appear in the wage equation. In this case, we must assume that the non-wife income and the kids less than 6 years old have no effect on wages after controlling for education, experience, and race. In Part 5, compute the inverse Mills ratio for each observation and add it as an additional regressor to the wage equation from Part 2. What is its two-sided p-value? Do you think this is particularly small with 3,286 observations? After the probit regression for the labor force participation, we can compute the inverse Mills ratio, lambda hat. The inverse Mills ratio is defined as the ratio of the standard normal density of the fit value divided by the standard normal cumulative distribution function of the fit value. So we first use the predict command and XP option to obtain the fit values labor force participation hat, and then compute the inverse Mills ratio for each observation. Finally, we add the inverse Mills ratio lambda hat to the wage equation. The two-sided p-value for the inverse Mills ratio is 0.077. It is statistically significant at the 10% level. It is evidence of endogenous sample selection. In Stata, we can use the Heckman command to do the sample selection corrections instead of doing it manually. We type Heckman followed by the wage equation. After the comma, we write the option select and put the selection equation into a parenthesis. We use the two-step option to specify the Heckman two-step procedure and the Mills option to store the inverse Mills ratio. We can verify that the inverse Mills ratios from this command and those by hand are identical. In Part 6, does adding the inverse Mills ratio change the coefficients in the wage regression in important ways? Explain. We can compare the estimates in a table. We have used the estimates store command to store the estimates for each model. Now we use the stab command to list the estimates in a table. Adding the inverse ratio does not change the coefficients in important ways. The return to education increases slightly from 0.099 to 0.103 after sample selection corrections, but the difference is not substantial. We remember that the inverse Mills ratio in the wage equation is only significant at the 10% level. It is not significant at the 1% or the 5% level. It implies that the sample selection bias is not severe. Let's solve computer exercise 12. In Part 1, the variable respond is a binary variable equal to 1 if an individual responded with a donation to the most recent request. The database consists only of people who have responded at least once in the past. What fraction of people responded most recently? We use the tabulate command for the binary variable respond. We find that 40% of people responded with a donation most recently. In Part 2, estimate a probit model for respond using whether to reply to recent mailing, the number of weeks since last response, the response rate to mailings, the number of mailings per year, and the average of past gifts as explanatory variables. Which of the explanatory variables is statistically significant? We use the probit command to estimate the probit model. Whether to reply to the most recent mailing is statistically significant at the 5% level. The number of weeks since last response, the response rate to mailings, and the number of mailings per year are statistically significant at the 1% level. The average of past gifts is insignificant, with a p-value of 0.317. In Part 3, find the average partial effect for mails per year and compare it with the coefficients from a linear probability model. We use the margins command and the dy/dx option to obtain the average partial effect of the mails per year on the probability of donation response. It is 0.046, implying that one more mailing per year increases the probability of donation response by 0.046 or 4.6 percentage points, holding the other variables in the model fixed. By contrast, the linear probability model gives an estimate of 0.052. In Part 4, using the same explanatory variables, estimate a Tobit model for gift, the amount of the most recent gift. Now, which explanatory variable is statistically significant? We use the Tobit command to estimate the Tobit model for gift. The variable gift contains zeros for more than half of the observations and is continuous for the positive values. Zero donation is a corner solution response. It is appropriate to use the Tobit model. We specify the corner solution value using the lower limit option. Now, whether to reply to the most recent mailing becomes insignificant at conventional levels with a p-value of 0.215. The other four explanatory variables are statistically significant at the 1% level. In Part 5, compare the Tobit average partial effect for mails year with that from a linear regression. Are they similar? We use the margins command to obtain the Tobit average partial effect. It is 1.49. The average partial effect from linear regression is the coefficient on the variable 1.99. They are not similar. In Part 6, are the estimates from Part 2 and Part 4 entirely compatible with each other? Explain. In Part 2, we use a probit model for the binary dependent variable, the donation response. In Part 4, we estimate a Tobit model for a continuous variable with corner solution values, the amount of the donation. The dependent variable is different between these two models. We cannot directly compare the estimates, but we see that the signs of the estimates are the same. They are compatible. Let's find answers to computer exercise 13. In Part 1, using OLS on the full sample, estimate a model for log wage using explanatory variables, education, ability, experience, the three region dummies, and urban. Report the estimated return to education and its standard error. According to the OLS regression, the estimated return to education is 0.104. Its standard error is 0.010. The t-statistic is 10.70, and its p-value is 0 to 3 decimal places. In Part 2, we estimate the equation from Part 1 using only people with an education of fewer than 16 years. What percentage of the sample is lost? Now, what is the estimated return to a year of schooling? How does it compare with Part 1? If we estimate model with people with an education of fewer than 16 years, the sample size reduces from 1,230 to 1,064. We lost 166 observations. It's about 13.5% of the total observations. The estimated return to education is 0.118, and standard error is 0.013. The effect is larger than that in Part 1. In Part 3, drop all observations with a wage greater than or equal to $20, so that everyone remaining in the sample earns less than $20 an hour. Run the regression from Part 1 and comment on the coefficient on education. We estimate the model by OLS for observations with a wage of less than $20. The estimated coefficient on education is 0.058, much less than that with the entire sample, 0.104. In Part 4, apply truncated regression using the sample in Part 3. The truncated regression appeared to recover the return to education in the full population, assuming the estimate from Part 1 is consistent. Explain. Using the truncated sample, we estimate a truncated regression model. We use the trunreg command and the upper limit option to specify the upper truncation point. The truncated estimate for education is 0.106. It is close to the return to education in the full population, 0.104. We can see it clearly by comparing the estimates in the table. Let's do computer exercise 14. In Part 1, we estimate a probit probability model relating very happy to those who occasionally attend churches and regularly attend churches, and include a full set of year dummies. Find the average partial effects for the two dummy variables. How do these compare with those from estimating a linear probability model? We can use the probit command to estimate the probit model for the dummy dependent variable very happy. Then we use the margins command and the dydx option to obtain the average partial effects. The average partial effect of occasionally going to churches is not statistically significant. The average partial effect of regularly going to churches is 0.107. It is statistically significant at the 1% level. For the linear probability model, we use the regress command. The coefficients on the variables in the linear probability model are the average partial effects. The average partial effect of occasionally going to churches is close to that of the Tobit model and insignificant at any reasonable level. The average partial effect of regularly going to churches is 0.112, slightly higher than that of the probit model and significant at the 1% level. In Part 2, define a variable high income equal to 1 if family income is above $25,000. Include high income, unemployed 10, education, and teens in the probit estimation in Part 2. Is the average partial effect of regular attendance affected much? What about its statistical significance? We generate a dummy variable, high income. It equals 1 if the family income is greater than $25,000. It's 0 otherwise. We estimate a probit model with the two attendance variables, high income, unemployment, education, and whether having teenagers in the household as explanatory variables. The average partial effect of regular attendance is 0.100. It is statistically significant at the 1% level. The average partial effect drops from 0.107 to 0.100. It does not change much. In Part 3, discuss the average partial effect and statistical significance of the 4 new variables in Part 2. Do the estimates make sense? We use the margins command and the dydx option for the 4 new variables one by one. The high-income people's probability of being very happy is about 3 percentage points higher than low-income people. The unemployed people are 10 percentage points less very happy than employed people. 1 more year of education is estimated to increase the probability of being very happy by 1 percentage point. The above 3 explanatory variables are statistically significant. The number of teenagers in the household does not significantly affect happiness. All the estimates make sense. In Part 4, controlling for the factors in Part 2, do there appear to be differences in happiness by gender or race? Justify your answer. We add the female and the black dummy variables to the probit model and then use the margins command to obtain the average partial effects. We find that happiness does not differ by gender, but it significantly differs between black and non-black people. Black people are 7 percentage points less very happy than non-black people, holding all the variables in the model fixed and accounting for the year fixed effects captured by the year dummies. Let's find answers to computer exercise 15. The data on 9,822 men include labor market information, whether the man abuses alcohol, and demographic and background variables. In this question, you will study the effects of alcohol abuse on employment, which is a binary variable equal to 1 if the man has a job. If employment equals 0, the man is either unemployed or not in the labor force. In Part 1, what fraction of the sample is employed at the time of the interview? What fraction of the sample has abused alcohol? We use the tabulate command for the binary variables. 89.82% of the sample is employed at the time of the interview. 9.92% of the sample has abused alcohol. In Part 2, run the simple regression of employment on abuse and report the results in the usual form, obtaining the heteroscedasticity robust standard errors. Interpret the estimated equation. Is the relationship as you expected? Is it statistically significant? The linear probability model gives a slope estimate of minus 0.028. The robust standard error is 0.011. The t-statistic is minus 2.54, and its p-value against a two-sided alternative is 0.011. It implies that the men who abuse alcohol are 2.8 percentage points less likely to be employed on average. The sign is expected. The effect is statistically significant at the 5% level. In Part 3, run a probit of employ on abuse. Do you get the same sign and statistical significance as in Part 2? How does the average partial effect for the probit compare with that from the linear probability model? The probit model gives similar results. the average partial effect is 0.026, and it is statistically significant at the 1% level. In Part 4, obtain the fit values for the linear probability model estimated in Part 2 and report what they are when abuse equals 0 and when abuse equals 1. How do these compare to the probit fit values, and why? We use the predict command and the XB option after the linear probability model to obtain the fit values of employment. The fitted employment probability is 0.901 when abuse is 0, and it is 0.873 when abuse is 1. The probit model gives the same fitted values. In Part 5, to the linear probability model in Part 2, add the variables age, age squared, education, education squared, married, family size, white, northeast, midwest, south, central city, outer city, quarter 1, quarter 2, and quarter 3. What happens to the coefficient on abuse and its statistical significance? We compare the estimates in a table. The size of the effect drops slightly from 0.028 to 0.020. Its significance drops to the 10% level. In Part 6, estimate a probit model using the variables in Part 5. Find the average partial effect of abuse and its t-statistic. Is the estimated effect now identical to that for the linear model? Is it close? They are not identical. The average partial effect is minus 0.019, which is close to that of a linear probability model, minus 0.020. The t-statistic is minus 2.13. It is statistically significant at the 5% level. In Part 7, variables indicating the overall health of each man are also included in the dataset. Is it obvious that such variables should be included as controls? Explain. On the one hand, the 3 health dummies are individually significant at the 1% level in the probit model. They should be included in the model because they are significant determinants of employment. On the other hand, overall health is correlated with whether the man abuses alcohol, and it could be the result of alcohol abuse. If this is the case, it causes over-controlling if they are included in the model because we cannot hold them fixed when studying the ceteris paribus effect of alcohol abuse. We can check the correlation coefficients between alcohol abuse and health dummies. Alcohol abuse is not highly correlated with health dummies. It implies that the health variables represent factors other than alcohol abuse. I tend to add them to the model. Notice that the inclusion of the health dummy variables reduces the alcohol abuse effect on employment. In Part 8, why might abuse be properly thought of as endogenous in the employment equation? Do you think the variables mother alcoholic and father alcoholic indicating whether a man's mother or father were alcoholics are sensible instrumental variables for abuse. First, there exist factors that affect employment and correlate with alcohol abuse in the error term, such as personality and family background. The omitted variable bias is one source of endogeneity. Second, alcohol abuse could influence employment probability, but the reverse is also true. Unemployed men could be more likely to be addicted to alcohol. The causality is simultaneous. Reverse or simultaneous causality is the second source of endogeneity. To become a valid instrument variable, it should satisfy two requirements: the instrument relevance requirement and the instrument exogeneity requirement. The first can be verified in the reduced form equation for alcohol abuse. The Probit model shows that the two parents alcoholics variables are statistically significant at the 1% level, so they satisfy the instrumental relevant requirement. We can argue that whether a parent is addicted to alcohol should not directly affect the child's employment or correlate with the error term in the employment equation after controlling for the variables in the model. The instrument exogeneity requirement should be met. In Part 9, estimate the linear probability model underlying Part 5 by two-stage least squares, where mother alcoholics and father alcoholics act as IVs for abuse. Is the difference between the two-stage least squares and OLS coefficients practically large? We use the IV regress command to estimate the model by two-stage least squares. The difference between the two-stage least squares and OLS coefficients is practically large. The alcohol abuse effect on employment becomes much larger by the two-stage least squares. The men who abuse alcohol are 30 percentage points less likely to be employed. The 95% confidence interval for the two-stage least squares estimate is much wider than that for the linear probability model. In Part 10, use the test described in section 15.5 to test whether abuse is endogenous in the linear probability model. We use the estat endogenous command to test for the endogeneity. The p-value is 0.03. We reject the null hypothesis that the variable is exogenous and conclude that alcohol abuse is indeed endogenous. We can also perform the endogeneity test manually, as described in the textbook. As a review of the endogeneity test, we first estimate the reduced form equation for alcohol abuse and obtain the residuals mu2 hat. Then we add mu2 hat to the structural equation and find that mu2 hat is significant at the 5% level. It gives the same conclusion. The abuse variable is endogenous. Therefore, the two-stage least squares estimates are more consistent than the OLS estimates. Let's do computer exercise 16. In Part 1, for the OLS estimates reported in Table 17.5, find the heteroscedasticity robust standard errors. In terms of the statistical significance of the coefficients, are there any notable changes? We estimate the OLS model and the Poisson model with the usual standard errors and the heteroscedasticity robust standard errors. Then we compare the estimates in a table using the stab command. The robust standard errors are generally larger than the usual ones, but there were no notable changes in the significance. In Part 2, we are asked to obtain the fully robust standard errors. Since the fully robust standard errors are applied to the cluster data, we cannot use the method here. In Part 3, compute the average partial effects for each variable in the Poisson regression model. Use the formula for binary explanatory variables for Black, Hispanics, and Born 60. Compare the average partial effects for Employed 86 and Income 86 with the corresponding OLS coefficients. We use the margins command and dydx option to obtain the average partial effects after the Poisson regression. The average partial effects in the OLS regression are just the coefficients. We can compare the results. One noticeable difference is the average partial effect of the number of quarters employed. The average partial effect from Poisson regression is minus 0.015, and it's not significant at the 10% level, but it is minus 0.051 in the OLS regression and statistically significant at the 1% level. In Part 4, compare the robust t-statistic for the OLS estimate of the beta for the proportion of prior convictions with that in the Poisson regression. The average partial effect of prior convictions on the number of arrests is minus 0.162 from the Poisson model. The effect is minus 0.132 from the OLS model. The robust t-statistic for the former is minus 4.02 and the latter is minus 3.93. They are similar. Let's solve the last computer exercise for this chapter, number 17. In Part 1, how many observations in the sample have earnings equals 0? Is it a large percentage of the sample? We use the summarize command and the count command to find information on the variable. Of 1,130 observations, 194 earned 0 in 1998. It is about 17.2% of the total observations. It justifies using the Tobit model that considers the corner solution value. In Part 2, estimate a Tobit model for N98 using chain, N96, education, and merit as the explanatory variables. Report the beta hat for chain and its standard error. Is the sign what you expect? How statistically significant is it? The beta hat is 3.75. Its standard error is 0.54. The positive sign is what we expect. The training helps increase earnings. In Part 3, does it make sense to compare the magnitude of the Tobit coefficient beta hat chain with the OLS coefficient from running a linear regression, say gamma hat chain? Explain. We cannot directly compare the magnitudes of the coefficients. The average partial effects in the OLS regression are the coefficients estimates, while the average partial effects in the Tobit model are the estimates times a scale factor. We use the margins command in Stata to obtain the average partial effects after the Tobit regression. The average partial effect of chain on earnings is 3.16 from the Tobit model. The average partial effect is 2.90 from the linear model. In Part 4, obtain the average partial effect of chain and obtain its standard error. How does it compare with the OLS estimate? We have already obtained the average partial effect of chain 3.16, and its standard error is 0.45. The effect is statistically significant at the 1% level. The OLS coefficient is 2.90, and it is also significant at the 1% level. In Part 5, estimate the Tobit model, including a full set of interactions of chain with U96, education, and merit. Now compute the average partial effect of chain, along with the standard errors. How does it compare with the linear model with full interactions in example 7.13? The linear model in example 7.13 gives the average partial effect of 3.11 and is statistically significant at the 1% level. The Tobit model here gives the average partial effect of 3.33, slightly higher than that from the OLS, and it is also statistically different from 0 at the 1% level against a two-sided alternative. Thank you so much for doing the computer exercises with me. See you soon in the next chapter. Thank you for watching this video and subscribing to my YouTube channel. See you next time.